applications for exponential growth and decay and logarithmic growth and decay. So we're splitting it up into 2 days. So today we're going to be looking at just models for exponential growth and decay, and Wednesday we'll be looking at logarithmic models. So anybody that's taking chemistry 111 or 112 or about to, you know that in chemistry you deal with an idea called the pH of substances, which are uses logs. So this will help you if you're planning on taking chemistry. So again, remember about your projects either Wednesday or Friday this week. Our final is next Wednesday in this room at 10:30. Okay, in this room at 10:30. Okay, so let's take a look at these two models. We're saying that if you're trying to do some type of use a model for exponential growth or decay, then you can use either of these two models at their equivalent. Okay, so let's kind of pull these out and take a look at them. The first model, F of t equals a sub naught times b to the t, looks just like our regular exponential we've been studying. Remember, we've been looking at things like this, a times b to the x. Okay, so that looks just like our regular exponential where a is some type of vertical stretch or vertical shrink, okay, of the original parent function b to the x. So now we're just saying that the coefficient of b to the t is a sub naught. And if you remember why we use that particular notation, a sub naught represents the initial amount. It's the amount at time t equals 0. That's why it has that little t sub naught. All right, it's the initial amount. B is either your growth factor if b is greater than 1, right? If b is greater than 1, it's going to be a growth factor. And if b is between 1 and 0, then b will be a decay factor. So that's like when we're looking at half-lives or populations that may be decreasing versus increasing. Okay, anything that shows a decline in growth is your decay factor. Okay, so that's sort of what all of that notation means, where t represents the number of years or minutes, okay, some unit of time, right? Seconds, okay, etc., some unit of time. All right. So now we're saying that this formula is equivalent to this formula, that these two things are absolutely the same, and it doesn't matter which one you use. So let's take a look at this new formula. Well, in both of them, you can see they both use a sub naught, the initial amount. But the next formula, or the next model, has e in it, the constant e for the base, okay? And so the question is, how are these two things the same? Well, if you were to compare them, if you set them equal, a sub naught times b to the t, if you set them equal, you notice that a sub naughts will cancel. If you divide both sides by a sub naught, you get b to the t equals e to the kt. Right? Now, if you take the natural log of both sides, okay, the exponent comes down in front, multiplies the natural log of b, which is just a constant. This exponent comes down in front times the natural log of e. Well, the natural log of e is just 1 because you have the same base here. You just pull off the exponent, so that's just a big fat 1. Okay, so the t's cancel, and so k is equal to the natural log of b. So this value right here, which is called your instantaneous or continuous growth rate, or your instantaneous or continuous decay rate, is just the natural log of b. And that's what's given right here. K is the natural log of b. For some reason, this isn't oriented, so I'm writing, and it's writing like to the left of where I'm writing. So if K equals the natural log of B, that's, if you want to put this in exponential form, what's the base of my log here? What's the base of the log, even though you don't see it? E. If it was 10, it would say log with no number. Okay, so e to the k equals b. So you can go back and forth between these two formulas. So remember, b is what's used here, and e is the base here, where k is the natural log of b. You can go back and forth between these two formulas. If you know b, you can find k. If you know k, you can find b. So these will be the two equations that you'll be using throughout today's work. So this is the formula you would use if your problem told you the instantaneous or continuous growth rate. So if you know the continuous, either growth factor or decay factor. So if you know that, that's going to be what we call K. So if you're reading a problem and it tells you the continuous growth factor is blah, 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 then you know you use this. If it just tells you the growth rate or the decay rate, then you use your first one. Okay, so those of you who are studying business, I know a lot of you are BAT majors, this is equivalent to your formula for continuous interest rate. Go ahead, Sam, I'll wait till you do that. Okay, this looks just like your formula for continuous interest, right? Let's take a look at this for a second. This formula, it's just that your letters are different. A sub naught times e to the kt. For those of you who know interest, the amount of money you have, A sub t over a certain amount of time, looks like this. This is continuous compounding. So this is the formula you use for continuous compounding of interest. Right? And notice the only difference is we call the initial amount the principal. That's the amount that you're looking at the growth of. How much will, say, $1,000 grow with continuous compounding, which is what most banks do, after a certain number of years, okay, with a particular interest rate. So notice P and A sub naught are the same. Your E's are the same. So your K and your R is the rate of growth in this particular case for money. All right. So many of you are familiar with that formula. It's called, I just say, remember that green shampoo, the green bottle, PERT, P e to the RT. So that's how you could always remember the formula for a continuous compounding of interest, PERT, P e to the RT. So for our purposes, P is now just A sub naught, K is replacing R. It's the continuous growth factor or decay factor. So let's look at this. I found this problem a few years ago, and I thought it was an interesting problem. I found it, I was reading a paper. So you want to read this for us, Shane?
In 1976, approximately a quarter of a billion gallons of bottled water were sold in the United States. In 1976, 20,000 bottled water
Okay, so this word epidemiology is a study of epidemics in the population. Okay, so that's what that long word means, epidemics. It's a study of epidemics. So I got this information from an article I was reading, and it was an environmental article because plastic bottles are an environmental problem. And they show up everywhere, including in Indonesia in the water systems because of something called the Pacific Gyre. If you haven't looked this up, put that on YouTube and take a look at that. It's very scary. In terms, yes, yeah, huh? Yeah, and they had this particular one that I watched, I used to show it to my classes at this point, and there's a turtle that has, you know, the plastic band from a six-pack wrapped around its waist. Of course, they call the turtle Mae West, but it's very sad. All the autopsies done on like the wildlife, like birds and stuff, show like plastic cigarette lighters in their bellies and all sorts of stuff. And then there's a sort of like a whirlpool effect in the Pacific Ocean that takes all of the trash and it deposits it. You see people in their countries, like, you know, rowing down the river or the waterways, and it's just filled with plastic bottles, and it's really depressing. So make sure you're in a good mood to watch it. But it's also an important issue about why there's been so much work done in our country anyway to try to move away from plastic bottled water. I felt so bad because one year I was talking about this and I had like 2 or 3 students in class with plastic bottles of water. So what, huh? No, that these things that, no, I'm talking about the ones you actually purchase, you know, and then you have to dump them. But if you recycle them, that's important. It's just that a lot of these things, unfortunately, don't get recycled, right? So let's construct 2. So you can see that these 2 models are equivalent. 2 equivalent models that represents bottled water sales between 1976 and 2000. So what's going to be our initial year here based on what you've just read and heard? What will be the initial year? 1976, right? So our initial year will be 1976. So 1976 is what we're going to call T equals 0. So T itself will represent the number of years after 1976. So we have 2 models we're looking at. The first model, I'm just going to change F of T to A of T if you don't mind, just because I'm thinking about the quantity of bottles. So A of T, well, I'll keep it F of T just so you don't get confused. I don't want to change anything on you really. F of T, so what's our first model say? What we're sort of used to, some initial amount times B to the T. Okay, now second model is when we have continuous growth. So F of T equals A sub naught times E to the KT. Again, that's PERT, P E to the RT. All right, so F of T is going to represent the number of bottles of water sold after T years. Anything else we need to know here? What else do we need to know? Do we know A sub naught? Do we know the value of A sub naught? A sub naught goes along with T equals 0. So what year was T equals 0? 1976. Do we have the value? Do we know how many, the number of bottles of water that were sold in 1976? 250 million, right? So A sub naught is the number of bottles of water sold in 1976. Well, I don't want to write out 250 million. I'm just going to write out 0.25 like that to make my numbers a lot smaller to work with, where we know it's in billions, right? So up here, when I defined F of T, I should have put my unit in here in billions. Okay? So I know that that's 1/4 of a billion. That's my unit. Okay, so now I go back and I see my problem gives me the continuous growth rate. The continuous growth rate is the value of K. K equals 0.12. So that's what I put right in here for K. So I can figure this out now. I can write my model. Here's my model using a continuous growth rate, 0.25. That represents my 250 million in 1976 times E to the 0.12 T. So there's my model. You tell me T, and I'll tell you what the prediction is or the estimate is for that year, how many bottles of water was sold in billions. Okay, if I want to use my first model, I have to convert K to B. Okay, I have to convert K to B. K is the natural log of B. So K equals the natural log of B. Right, that's the first thing we have. And B equals E to the K. Those are the two formulas we're working with. So to find B, we just take E to the K. We know what K is. K is given to us right here, 12% continuous growth rate, 0.12. So we put that into our calculator. We can get an approximation for that. We just go back here and say, okay, let's clear this all out. So we go second natural log, and we put in 0.12, and there's our value for B. That's our base, 1.127496852. I'm going to put as much of it into my model as I can so I can be as accurate as possible. A sub naught hasn't changed. It's still 250 million bottles of water. Now, my base is 1.127496852 raised to the T. So that's my second model. And both of these are exactly the same. If you put both of those in, you put this into Y1 and this into Y2, and you do a table for them, your answers will be exactly the same. Now, if you round off B like to 1.13, your numbers will be off a little. So if you were putting this into your calculator, you want to store this number. So let me show you, like, you want to keep all of this, E to the 0.12. So you want to store this number. You hit your button right here, your store button. This is taking the place of B. So why not call it, let's store it in B. So you hit the store button, and you say, I want to take this answer or this value, E to the 0.12, and I want to store it in B. So you hit the store button, and then you press alpha B right here. See the little green B? Alpha B, and you hit enter. So now, whenever you want to use that value, you just press your B button, alpha B. So let's suppose I want to put these two, let's clear this out. I want to put these two models into my calculator. So my first model is 0.25 times E to the 0.12 times X. That's my first one. Now, this one is supposed to be totally equivalent. Again, if you round this off at all, your numbers are going to come out different. So I've put this number, E to the 0.12, under the name B. So now when I put it in here, I'm just going to do this, 0.25. I'm going to recall B back again by hitting alpha B. Whoops, I hit alpha C. All right, alpha B. There it is. So now I'm not going to be truncating it or getting any rounding error, and that's raised to the X power. That's raised to the X power. Where's X? There it is. Okay, so now let's start this table at year 0, which represents 1976. So I'm going to start my table at 0, and I'm going to increment by a year. And let's have this table increment automatically so you can see that the values are the same. See, the values are exactly the same here. Okay, so it looks like I've got something wrong here. What's going on? Didn't I start at 0? 0. Oh, that was the other. There we go. So these represents the number of billions. Okay, bottles of water. All right. So these two formulas, it doesn't matter which one you use. So let's take a look at making a prediction. Why am I calling it a prediction if I'm looking at 2002, the number of bottled waters in 2002? Why am I calling that a prediction? Right, because my model, my continuous growth factor was only from using the data from 1976 to 2000. So I'm extrapolating, I'm going outside of my data set now. So let's use both of these models and extrapolate and predict what the sales will be. How many bottles of water will I be selling in the year 2000? So the first thing I have to do is find my value of T. And what's my value of T going to be here? 26, because that's 2002, take away 1976 is 26 years. Okay. So A sub naught hasn't changed. It's still 0.25 billion. Okay. So let's use our continuous. I keep using A because I'm so used to using A when that's A. The F of T just doesn't work for me. But anyway, F of 26. So let's find how many billions of bottles of water was sold in 2002, at least the prediction. Okay. So we say 0.25 billion times E to the 0.12 times 26 years. So let's see what that is. So we go into our calculator. Something is wrong with what I input in here, I think. Let me see. That's not exactly, oops. There it is, okay. So notice we can either do this out, or once you input your equations in, you can use your tables and there's your answer. The answer is 5.6616, okay, which if you estimate is 5.7. So our model is predicting that in 2002, 5.7 billion gallons of water were sold. 5.7 billion approximately. So that's using the continuous rate. Again, you can use your other formula, F of 26, which is 0.25. And what did we say B was? B was this long number, 1.127496852 raised to the 26th. Okay? But as you know, we already have that in our y equals, and here's the same exact answer. You're not going to get any different answer by using the other formula because they're exactly equivalent. 5.7. Okay. So this model is predicting that in 2002, 5.7 billion bottles of water. I don't even know if you can imagine how many bottles of water that is. It's like one of those things, if you stacked pennies and you had this many pennies, where does it go? I mean, I think large numbers just, you know. Mm-hmm. Yep. Well, it depends on what's the size of the individual bottles. 16. Mm-hmm. Or a lot of them are liter bottles too. Okay, so you at your seats use whatever model you want. It would be great if one person at the table could use one model and another person could use another, and find out how many bottles of water this model predicts for 2007. Okay, for 2007. Thanks, Julia. If we actually look at our model now our model is predicting that in 2007, 10.3 billion bottles of water. So this is the prediction. The actual number of gallons that were sold was 8.82. So the actual data point for 2007 was 8.82. So as you can see, our model is now overestimating the actual number of gallons of water that were sold. And that's because in 2007, we saw our first decline. Between 2007 and 2008, the bottled water industry saw its first decline in the number of gallons of water sold, and it's been declining ever since. So this model may have been good for 2000 and maybe slightly after 2000, but beyond that, it's going to not be a good model. It's going to break down because it continues to grow exponentially, and the I can't say that. Bottled water industry has since seen a decline in its products sold. So this is a little different type of problem though now that I'm asking. Let's see how we would set this up. Let's use our model with continuous growth. Let's use this model and see how we would do this problem. Okay, so this problem says when, so when it asks for when, which of our variables are we now solving for? We're solving for t, time. So that means we're going to have to use all of the techniques we learned earlier for how to solve an equation that has an exponential in it, exponential equation. So we're trying to solve for t now. So we're not plugging the value for t in, we're actually trying to find the value of t. So when does the model predict the sales of bottled water? When does it predict that these sales will reach 100 billion gallons? So where does the 100 go, the value 100? What do I substitute for 100? Right here. When will that value be 100 billion gallons? So you put 100 in. A sub naught hasn't changed. It's still 0.25 e to the 0.12 t. So no, t is not 100. T is what we're trying to solve for. We're trying to figure out how many years. 100 represents the amount of bottled water. Go back here. Right? F of t is the number of bottles of water. It's actually the number of gallons of bottled water. That's where I made my initial mistake. It's a number of gallons of bottled water. So right here, Shane, when they say 100 billion gallons, that's the value here. This is the value we were getting once we knew what the year was before, right? We were putting like 26 and 31 in here, and out popped the number of billions of gallons. So now we know, we're trying to figure out, when will we be selling 100 billion gallons of water? So we got to solve this equation. So you want to isolate your exponential. You want to isolate that. So you divide both sides by 0.25. That gives you a nice 1 right there. And 100 divided by a quarter is 400. Equals e to the 0.12 t. And we want to get t out of the exponent there. And we want to bring it down, sort of like thinking about typing, or it's now a superscript. We want to bring it down. So we have to take the log of both sides. Which one? Doesn't matter, but let's take the natural log. Natural log of 400 equals the natural log of e to the 0.12 t. Okay, so the natural log of 400 is just a constant. We use our log properties, and this exponent comes down out in front, and we get the natural log of e. Well, the natural log of e is just 1, because if you lift off that exponent right there, your bases are the same, you just get 1. So now we have the natural log of 400 equals 0.12 t. And to solve for t, I divide both sides by 0.12. So t is equal to the natural log of 400 divided by your continuous growth rate. So let's see what that is. How many years is it predicting it will be 100 billion? About 50 years, right? It's 49.9. So t is approximately 50. So that's saying in 2026, our model predicts that 100 billion gallons of bottled water will be sold. What do you, no, it's 50 years after 1976. Just that year, yes. Okay, but what do you think about that prediction based on what we just saw in the problem before it? No, it's not accurate, because we've already seen that the bottled water industry has seen a decline in sales. So that would be pretty scary, because that's not too far from now, 2026. You'll all be old and gray, right? But anyway, You won't be actually. So it's not I'm using this basically to show you or to review with you how you solve an exponential equation, right? This is what we did last week. So that's sort of using that first problem and looking at that. The emphasis of your book on this section is on population growth. And population growth is an important problem to look at. I shouldn't call it a problem. In some places it's a problem, but as a world it is a problem, our population growth. And so similarly, you can use these two models to represent population growth. Doesn't matter which one you use. So your book gives you a bunch of countries with their population, and Caitlin did a little research and actually selected these 1, 2, 3, 4, 5, 6 countries with the population in the year 2010. And then depending on which model we pick, it's either going to give you the annual growth rate, that's what B is, the annual growth rate or the annual growth decline, or the continuous growth rate. And you can work, you have the flexibility now to go from one model to the other. So let's do a couple of these together. So notice if you were just comparing the first 3 countries here, the United States, Liberia, and Qatar, can you look at that third column and tell me which country has the largest annual growth rate? Qatar. And what is that annual growth rate? Almost. They all start with 1, and that's because if you think of how interest works, right? You take your original principal amount, and then you take whatever you're earning for interest, R times P. So if you pull the P out, you get 1 plus R. You're always going to get this factor 1 plus R. So if your interest rate is 5%, that would be 1.05. So when you look at that annual growth factor, you just look at the decimal to get your percentage, okay? Because they're all going to be 1 point something here, right? So if you take off what would be the annual growth rate here for Qatar? 11.2%. What would it be right here for Liberia? Move that 2 places, 3.5%. And then for the United States, what is it? It's 0.9%. It's less than 1%. Our population growth rate is less than 1%. It's 0.9%. Okay, so Qatar is growing really fast. It clearly doesn't have as many people as we do, but it's growing at a pretty fast rate. Let's go down and look at China. Go down and look at China. Now, this is a continuous growth rate. We'd have to convert it back to compare it to the United States. So let's do this. This is the value of K. How do we go backwards to get the value of B? What do? E to the K. So let's find what the annual growth rate of China is by doing E to the K. So let's get our calculators out. And we just say E to the K. So let's quit this all and clear everything. So we say E raised to the 0.00499. Oops, I got two things in there. 0.00499. And there's my annual growth rate. 1.005002471. So China's growth rate, if you ignore the 1 and you move the decimal point 2 places to the right, is 0.5% a year. Okay? Now, remember, exponential growth is directly proportional to your population. So even though it's growing at a slower rate than the United States, look at how many millions of people it has. 1,338.1 million. That's 1,338,000,000 people. Okay. So this will probably change because I don't know if you've heard recently, but China, many of you may be aware that they have a one-child policy. You can only have one child. They put limits on the growth of the population. But just recent, huh? Yeah, well, boys are preferred, so that means, you know, what happens to the girls. But anyway, You can talk about that in your sociology class. So what's happened is they've now have generations of males that can't find wives because there's not enough women. So they've just recently, in the last 2 months, changed their policy back to now you can have 2 children. Supposedly in the rural areas, if you kind of grease the hand of the local officials, you've been able to have more than 1 child. So it's been it's an interesting sociological kind of situation. All right, so now you can now write, why don't you fill in these 2 right here so you can get the annual growth rates for Guatemala. But wait a minute, look at Germany. Is that a continuous growth rate for Germany? No. So that's a decline. So what kind of number are you expecting here? A number bigger than 1? No, a number between 0 and 1, right? It's going to be a decimal, because Germany's population is not growing. It's actually declining. It's the only country that I was able to find that had a declining population rate. So fill in these 2 right here by raising e to the k, and that will give you your rates for right there. And so table 1, I'd like you to get the continuous growth rate here. Well, I'll do the first one for you. The continuous growth rate is what? The natural log of this number. So k is equal to the natural log of 1.00969. So let's find that rate. Natural log of 1.00969, which is what? 0.0096433353. So if I use my continuous growth factor, or my continuous growth rate, f of t equals, for the United States, 309.6 million people as of 2010, times e to the 0.009433353t. Okay. So I'd like table 1 to do Liberia. Table 1. I'd like table 2 to do Qatar. And we've already done China and Guatemala and Germany. So table 3, I'd like you to fill in these spots right here. Table 4, I'd like you to do this. And Adam, I'd like you to do this. And then come on up, fill it in. All right. So I think we've been able to fill all these in based on the work of each table. And now see if you can match the country with each individual graph here. See if you can label which one's China, which one's the United States. This is your population in millions. And this is the number of years since 2010. Actually, notice I put it on here to tell you, so I'm glad you reminded me, since Caitlin didn't put it in. So we can tell Caitlin we gave her a check minus. So see if you can use the information you just got from your tables and label each of these. Notice how China looks like it's a straight line here, almost. Oh! Well, that would have been the easiest anyway, right? Because look at its initial population is your y-intercept, right? And it's got the highest population. So that's definitely China. Yeah, well, find the one that's not growing. Can't believe how much time I've taken here. Okay, so China is this first one here. And what's this one right here? United States. Okay. Qatar is right here. And so as I was pointing out, roughly 60 years from now, Qatar and China will have the same population, which is hard to believe since China right now has 1.3 billion and Qatar has 1.7 million, but that shows you the power of exponential growth. Qatar's growth rate is so much higher, 11.2% versus 0.005%, excuse me, 0.5%. Okay, and then where else did we go here? Well, here's Germany. It's the only one that's declining. Germany's right here. And then we have Liberia and Guatemala. Okay. All right, so let's take a look at decay. Similarly, you can show, just as I showed you earlier, that those two formulas that we just looked at were equivalent. You can show that these two formulas are equivalent. This first formula is the half-life formula where you know the actual half-life, the value of the half-life. It's m sub naught, which is your initial amount, your initial mass of whatever substance you're looking at. 1/2 because you're looking at a half-life. So if you start off with 100 grams of something and its half-life is, say, 2 billion years, then in 2 billion years you'd have 50 grams. Another 2 billion years you'd have 25, and it continues to decrease by a factor of 1/2. The exponent's t divided by h. It's equivalent to this model here where you have continuous decay, a continuous decay rate. And how do you know it's continuous? Because you see the constant E being used for your base. Whenever E is used for your base, you're dealing with continuous growth or continuous decay. So this model is m sub naught e to the negative RT, and R is equal to the natural log of 2 divided by H. So burial cloth of an Egyptian mummy is estimated to contain 59% of the carbon-14 it contained originally. How much carbon-14 did it contain originally when it was alive? Carbon-14 is used to date artifacts and fossils by what percentage of carbon-14 is still left. So if something's alive, what percent of carbon-14 does it have? 100%. So it has 59% of the original carbon-14 left. And we want to figure out how long ago the mummy was buried. Okay? So the half-life of carbon-14 is 5,730 years. So that's the value of H. If you want to use your continuous decay model, you have to find R. R is the natural log of 2 divided by the half-life. There it is right there. Now you can estimate it by throwing it in your calculator, or you can keep the whole kit and caboodle there. All right. So let's see. Number 7 says find the continuous decay rate of carbon-14. So let's do that right now. R equals the natural log of 2 divided by 5730. So let's pull up our calculators. Natural log of 2 divided by 5730 is approximately 0.000120968093. It's an exponent. It's in scientific notation here. Oh, here we go again. Ever since they've changed this, I've never gotten used to it. It's interesting how old habits die. All right, so there's that answer right there, natural log of 2 divided by 5730. Okay, so let's figure out how long ago this thing was buried. So again, we can use either one of these. Let's use the first formula. Here's the tricky part. What is the value of m of t, which is the mass of the substance remaining at time t? So we're trying to figure out how much of this mass is left. Well, m sub naught is the original amount. So how much is left at time t when it's discovered? Of what? 59% of what? That's just a number. It has to have some units now, folks, right? What was the initial mass? What's the value of the initial mass according to this formula right here? What's the value of the initial mass? That's the amount of carbon. What is the initial mass? M sub naught, right? Right here, initial mass, M sub naught. So when you found the mummy, it had 59% of its initial mass. Remember, percentages in these decimal equivalents have no units attached to them. So it's got to be 59% of some weight, some mass. Right, so when you now fill in this equation, it looks like this: 0.59 m sub naught equals m sub naught times 1/2 to the t divided by 5730. So you're trying to solve for t, folks. You're trying to solve for that value right there. So when you divide both sides by m sub naught, those cancel. So you take the natural log of both sides, 0.59 equals the natural log of 1/2 times t to the 5730. And this exponent comes down in front, t divided by 5730 times the natural log of 1/2 equals the natural log of 0.59. I'm running out of space. Hang on. Scoot this down here. Okay. So we multiply both sides by 5730, and we divide both sides by the natural log of 1/2. So on the left side, this is what we're going to have: the natural log of 0.59 divided by the natural log of 1/2 equals t. So you throw all that into your calculator. Thank God for calculators. Okay, and hopefully we'll all wind up with the same answer. Let me clear this out. So we have 5730 times the natural log of 0.59. And that whole thing, I better put this all in parentheses, so I'm going to get the answer and then divide it. Second answer divided by natural log of 1/2, which will also be negative, because between 0 and 1, your natural log functions below the x-axis, so you don't have to worry because you got a negative there. So about 4,362 years old. T equals 4361.75. So about 4,362 years old. Okay. Okay. So this is, I think if you've read any kind of articles about fossils found, you see this a lot, this kind of dating. Okay, and now quickly, the next two things are really for your information. Your book does a really nice job with logistic growth. As you know, when we were talking about the rabbit population, things don't grow forever and ever. There's limits put on growth because of resources, right, in the habitat. So often you'll have an exponential growth of a population, this blue curve. It grows, the rate growth is increasing, and then it starts to decrease, and then it reaches a horizontal asymptote. That's your limiting growth. That's your limit to growth. So sometimes if they feel that there's a particular animal, like in these national parks, that's growing too quickly, they'll introduce a predator, and then it slows down the growth rate. All right, so the asymptote here, the horizontal asymptote, the equation for that line, y is equal to this number right here in the numerator. Whatever the number in the numerator is, that's your growth. That's called the carrying capacity of your habitat. Carrying, when it's a situation in the wilderness, that's referred to as the carrying capacity, but that's your limit to growth. So it looks like a scary kind of formula, but it's not. It's just a division problem. C, A, and B are all just constants, and E is a constant as well. And the problem that your book gives you is one that deals with a flu epidemic, the spread of a flu epidemic in the population. And the numerator of a particular town where this epidemic is spreading is 30,000. So that value is the value for that horizontal asymptote right there. And the model that your book gives you is this, just so you can see it once. And it looks scary, but it's not hard to work with. This is the model for the spread of that flu epidemic. So if the question was, how many people had the flu when it was initially being recorded, the initial outbreak of the flu? What would be the value of t when you're looking at the initial outbreak? 0, right? That's the initial outbreak. So if you find f of 0, you just throw a 0 in. And this big, scary looking formula really reduces to something quite simple, because e raised to the 0 power is 1. So this just becomes 30,000 divided by 1 plus 20, which is about 1,429 people initially had the flu. Okay. So then you can ask, how about after 4 weeks? How about after 10 weeks? When will it reach 30,000? When will all people have the flu? So you can answer all kinds of questions like that now. So what I'd like you to do is I'd like you to turn to your group activity. And I just want to point out you have 2 problems. Number 2 works with the logistic model. You'll see this logistic model again, hint, hint. So make sure if you don't start there today or get to it, you work on it. And the first one is deals with an object that's cooling, and it follows something called Newton's law of cooling. So if I had a nice cup of hot tea and I put it right here on the desk, I could look at its temperature over time, and it would eventually reduce the horizontal asymptote would be the room temperature, right? Would eventually get very, very close to the room temperature. Anyway, have fun with those problems.